it off to Matteo. Matteo, do you want to take it over?
Yeah, thank you very much, Paige.
Yep.
So today I'll be presenting with my friends and colleagues. Dave, Michaela, and June, Fabio, and Theo. And basically our objective is to give you an overview of the ecosystem and the tools and libraries that we have been building around JAX, and to try to give you a feel and an understanding of why we as a group and as a company are quite excited about JAX, and also hopefully help answer some questions from you about maybe what are your doubts, what are your concerns, and whether or not JAX could be also useful for your own research and for your own projects. So let me start maybe with a very brief introduction to JAX, and to at a very bird's eye why it might be an exciting framework to work in and build machine learning projects and research on. So at its core, many of you will be already familiar, but let me just repeat really the fundamentals. At its core, JAX is a Python library that is designed for high-performance numerical computing. And among its key ingredients, it basically supports three main areas. One is differentiation, so forward and reverse mode automatic differentiation of arbitrary numerical functions. And here we have a whole lot of JAX primitives like grad, Hessian, Jacobian forward, Jacobian rev, that all allow you to basically implement and exploit the automatic differentiation capabilities of JAX. The second broad family of primitives that JAX offers to its users are related to vectorization and automatic vectorization. So in a lot of machine learning, we rely on a single instruction, multiple data style of programming, where we typically want to apply the same type of transformations to a whole batch of identical data. So we might, for instance, be computing a loss over a big batch of input and output samples. And JAX basically makes life a lot easier to researchers and practitioner of machine learning by exposing some very neat and simple abstraction to simplify single instruction multiple data programming. And these are mostly Vmap and PMap, and we're going to hear some examples today of how these can really make the difference in writing clean but expressive code. And finally, the third big area inside JAX is JIT compilation, so just-in-time compilation. And basically, JAX is built on top of XLA and uses XLA to just-in-time compile your code and make both faster your CPU code if you're running on CPU, but also give you transparent GPU or cloud TPU acceleration. The important feature of JAX, if you are to basically take away just one message from what is JAX, is that all these functions and these abstractions are implemented as composable program transformation. So what does this actually mean? Let's give a very, very concrete, simple example and consider a numerical function that just squares an input and sums to the second argument of that same function. You could write into Python this way, and x and y could be, for instance, NumPy arrays. The value of this function is, of course, evaluated like any Python function. You just call the function, pass some inputs, and the first input will be squared and summed to the second one. What would computing a gradient look like with JAX? Well, the neat thing of JAX is that the gradient of this function is also a function. So you just call jax.grad on a function, and you get back something that is still a Python object, is still a Python function, but that if you call, now computes the derivative of the original function in a very neat and transparent way. And importantly, this transformation is composable. So you could, for instance, compute the second order gradient by calling grad of the original function. And this, again, gives you just a Python function. But then if you pass x and y, gives you the second order gradient in those two values of x and y. Similarly, you can mix and match this with other program transformations like compilation. So if you just call JIT of grad of the original function, this gives you a compiled second order gradient function that, again, you can just call as any other Python function, but the first time you call it will trace the code and compile it using XLA. And then the second time, or all following times you will call the same function, it will execute the precompiled XLA code and therefore be much faster. And of course, this doesn't stop here. All the JAX primitives are neatly composable. So you could, for instance, batch and your function. You just write it as if you were just dealing with single examples. But if you Vmap that function, again, you get a function that now expects a batch of inputs and computes the same function on the entire batch. And finally, if you want to then execute these batched compiled second-order gradient calculation in parallel on multiple accelerators, for instance, this could be multiple GPUs, you just need to chain one more. Now you pmap a vmap to JIT grad of a function. And again, this is just a Python function that you can call on your inputs. And I hope this gives you a flavor of how composable gradient program transformations enable JAX to expose a very thin set of primitives that are easy to understand, but that you can then combine in very rich and very powerful programs that can support quite powerful use cases. And before I leave to my colleagues to delve into more details, I just want to conclude with a couple of final remarks on why JAX is so convenient. And I think there are a few things to remember. One is, of course, this composable nature of all its abstractions. But it's also good to remember that all of the numerical functions are written with a syntax that is fully consistent with NumPy. So it's literally you're literally just writing NumPy code, but then you can transform it using these program transformations. This means that JAX can be quite familiar even when starting, because Python and NumPy are widely used. And also, and a couple of points I want to highlight is one that is not a vertically integrated framework like many other ML frameworks. It's really focused on getting this core bit of numerical computing right, and then it still provides you with a very rich ecosystem built around it and a community around it that can give you the you can make other things and classical things like building neural networks easy for you. And this is what David is going to be talking about just now.
Hi, yeah, thanks a lot, Matteo. That was a great overview. So my name is David. I'm a research engineer at DeepMind, and I'm here today to talk a little bit about our DeepMind JAX ecosystem, which is essentially a collection of libraries that we've been developing together over the past 18 months or so now that build on top of JAX, as Matteo just been explaining, and sort of add additional functionality rather, specific for machine learning research. Next slide, please, Matteo. So why an ecosystem? So DeepMind researchers have had a lot of great initial success using JAX. So this is nominally a NeurIPS hosted event. Many of the papers that we're presenting at NeurIPS this year use JAX under the hood to produce the results. As engineers and researchers at DeepMind, we're constantly asking the question, how can we continue to support and accelerate this great work and this early success that we've seen? There are a few considerations that go into this. The first, as Matteo was just saying, is that JAX is not a vertically integrated machine learning framework. This is a strength. It does one thing it does a core set of things very, very well. And what we want to do is build on top of this and continue to build our own libraries on top to make this specific machine learning research and our particular needs. Whatever we build needs to support our rapidly evolving requirements, for instance, a specific focus on reinforcement learning, among other things. And where possible, we want to strive for consistency and compatibility with frameworks and tools that we've released in the past, for instance, that are compatible with TensorFlow, things like Sonnet and Truffle. The solution we've arrived at is an ecosystem, which is basically a collection of libraries of reusable and unopinionated JAX components. Each library is intended to do one specific thing well, and importantly supports incremental buy-in. So for instance, we're going to show you libraries for neural networks, libraries for optimization, for reinforcement learning. From day one, we've made sure to develop these in a way such that you can pick and choose the pieces you want without being locked into any decisions about other libraries or other tools from within the same library. And of course, where possible, open sourcing everything to enable research sharing and reproducibility of our results that we build on top of the JAX ecosystem. Next slide. I'm quickly going to go over 3 examples of libraries we've built, although there's others, and I encourage you all to check them out. For more details, we posted a blog recently on the DeepMind.com website that goes through this in more detail. So Haiku is our JAX library for neural networks. So as Matteo is highlighting, much of the strength of JAX comes from essentially this functional programming paradigm, whereby we have stateless functions and we can compose function transforms. So JIT of grad of Vmap of whatever returns a function, and that function can be statelessly applied to whatever, to some NumPy array or some JAX NumPy array. Often some abstractions that are common to machine learning, things like neural network trainable parameters and state, fit the object-oriented paradigm potentially better, or at least this is how people are used to thinking about this. So Haiku kind of tries to bridge the gap between the object-oriented world and the functional world of JAX. It essentially provides tools by which you can take stateful objects, such as neural networks, and convert these into initialization and application functions that can then be used directly in JAX. Our researchers have had great success trivially porting previous TensorFlow results, such as the alphas here, for instance, into JAX. And it's a widely used and mature framework, both within DeepMind, but more widely within Google and the public community as well. Next slide. OPDX. So OPDX is for optimization. So much like neural networks, it often makes sense to think about neural networks in an object-oriented paradigm as having state. OPDX is essentially a gradient processing and optimization library that at its core provides sort of a zoo of common optimizers that people know and love, things like SGD, atom, momentum, whatever it may be. And these are, importantly, these are defined as this chain operation of simple OPDX primitives, so sort of fundamental gradient processing primitives that are common to many of the optimizers and many other things as well. So OPDX provides these sort of simple out-of-the-box implementations, chaining these components together to build optimizers, and gives the user a lot of functionality to do this themselves. In addition, it provides a lot of useful utilities that allow the trivial application of gradient-based updates to neural network parameters. Not just haiku parameters, for instance, using out of the JAX neural network library, but sort of true to the spirit of incremental buy-in and cross-compatibility. All, or at least most of the popular JAX neural network libraries that you may be familiar with should be compatible with OPDX. Anything that represents the parameters as a tree of NumPy arrays, essentially. Again, widely used within DeepMind, but with a growing user base outside. Next slide, please. So, as you probably know, DeepMind cares quite a lot about reinforcement learning. I guess one of the complexities of reinforcement learning is it's very easy to get things wrong. For instance, if you place a stop gradient in the wrong place, which can be very simple to do, the entire experiment is going to fall apart. The idea of RELAX is essentially to provide a library of trusted, battle-tested reinforcement learning components. So not even algorithms, but subcomponents of algorithms. For instance, on the right-hand side, you can see how a Q-learning primitive and a square loss primitive can be combined to define a simple loss function that you might want to use. And essentially, this provides a substrate by which our researchers can use components that they trust and have algorithms that they trust, in addition to quickly contributing their own ideas back to be shared amongst the broader community. A lot of the emphasis we place on this library has been on readability. So for instance, what does this mean? We use Unicode everywhere. So if you have a look at our doc strings, we're not just scared to reproduce our doc strings to look like textbook examples, but also not being afraid to repeat ourselves as well. If we want people who land on a function for TD error to see what the TD error is and not need to chase this down 3 or 4 different functions. Next slide. So I don't have time today to go over all of the libraries that we've released as part of our ecosystem, but there are others. For instance, the Giraffe library for graph neural networks, which we released last week, as well as our checks library for testing and reliability. Here are some links here. I encourage you to check them out. In addition to this worldview that we're telling you today about an ecosystem, I suppose there's an additional shell around the outside of this, which are frameworks that are then built on top of these libraries. Some examples from DeepMind are JAXLine and Acme for supervised learning in RL. I encourage you to check these out. And in addition to the work from DeepMind that we've been talking about today, there's a lot of really great work being built on top of the JAX ecosystem, both within Google and in the public more generally. So for the rest of this presentation, I'm going to hand over to people who are going to talk more about their sort of research results that have been based on JAX and JAX ecosystem, starting with Mihaela, who's going to talk about GANs and generative models.
Thanks, David. So I hope everyone can hear me, and I'm super excited to talk today about what I think makes JAX amazing for generative models and specifically GANs. Next slide, please. And the reason I chose GANs is because they're a bit different than the standard view that we might have of other generative models of this paradigm of one model, one loss. In the GAN case, we have 2 models. We have the players, the generator, which is producing data, and the discriminator, which learns to distinguish between this generated data and the real data. And the goal of the discriminator is to be really good at distinguishing between these two, and the goal of the generator is to basically to fool this discriminator into thinking that the data that this generates is real. And the way to do this is either via a zero-sum game or via other types of losses. They don't need to be necessarily connected as long as the underlying principle is this. We have one player that learns to distinguish and one player that learns to fool, and hence the name adversarial. Next slide, please. Now, if we want to implement this in JAX, one thing that we notice straight off the bat is that when you implement again, you might want to do multiple discriminator updates for each generator update, or vice versa, often more of the discriminator. And this is super trivial in JAX. You just have to write a Python for loop for each of the players. We all know how to do that. And inside this Python for loop for each of the players, you decide to update the parameters of that player. And the really neat things about this that also Matteo highlighted earlier is that we now can get gradient functions. So not gradient values, but we can ask JAX, well, JAX, can I please have the gradient function, which is the gradient of the discriminator loss with respect to the discriminator parameters. And then I can evaluate that function at the current values of both of the discriminator parameter, generator parameter, and what other data batch I might have, and so on. And crucially here, there's no need for any stop gradient on the parameters of the generator, even though the value of that loss will depend on these parameters, because we just ask JAX for the gradient with respect to the first argument, which is the discriminator parameter. So this is very nice, very easy to reason about, and almost like a pseudocode. If you ask me to write a GAN algorithm pseudocode, it will look very similar to this. And I think this is really, really nice. Now, once we have the gradients, we can pass them to an optimizer, like an OPDX optimizer that David talked about, getting an update, getting our new discriminator parameters, and then doing exactly the same thing for the generator. This time only that we use a different loss, the generator loss, and we get a new gradient function, the generator loss function, gradient with respect to the generator parameters. So this is all very neat. Next slide, please. But one thing that I want to highlight here, we now have direct access to gradients. So for example, if I want to see how the norm of the gradients at different layers looks like, I can easily do that. I can just add 1 or 2 lines of NumPy code that I'm familiar with, and I can get those statistics. And I think this is very useful in terms of allowing us researchers to build intuition about what our models are doing in a very simple way. Next slide, please. Something else that I think is maybe specific to GANs that JAX highlights very nicely is it gives you more control, and it makes you think about the kind of decisions that you're trying to make. So one type of decision, for example, is, well, when I update the discriminator, what should I do about the generator state? And what I mean by state is not the generator parameters, but for example, let's say the generator batch norm statistics. Do I not want to update the statistics? And let's leave aside for now whether you actually want to do this or not in GANs. The point here is that when you implement GANs in JAX, it forces you to think about this, and it forces you to make the right decision. So briefly looking at this quick implementation that I made of the discriminator loss, we see that we have a for pass through the generator. This returns us a new generator state. And now when I return from this discriminator loss, I can say, well, I want to use this new generator state in conjunction with the new discriminator state, or next slide, please. I can just decide to ignore that and return the state of the generator that was given to me. Very, very easy. Again, I have to think what I want, and getting to what I want is just a matter of changing a few lines of code here too, instead of digging somewhere deep for something that I might not have access to. Next slide, please. And last but not least, I think I just want to say this one more time of this functional approach making code very close to math, especially in generative modeling when we often have a lot of distributions, gradients of things that depend on distributions, makes it much more easy to reason about. And I'm just going to highlight 2 things that Matteo talked about earlier, which is being able to vectorize functions and computing Jacobians. So if I want to compute let's say, gradients with respect to some parameters of an expectation of a distribution that depends on these parameters, this is non-trivial. We can use the score function estimator, but that has higher variance. And if we can, for some distributions, we can use the reparameterization trick. So this is just a trick that allows us to rewrite that expectation with respect to another distribution that doesn't depend on these parameters and push the parameters inside. Now, even with this new form, Now we see that we still have an expectation, so we have to compute some functions over multiple samples from this expectation. What we can do is we can expect the user to just always pass us in vectorized functions, which can be okay if it's only neural networks, but sometimes it can be something else. We don't only have to compute gradients with respect to neural network functions, or we can do it for them. And JAX really allows us to do that by just saying, well, I'm going to vectorize the function for you. You can pass in anything that you want. And I specifically find this very, very useful for tests, because even though we might use neural networks in our experiments, often we want to test for very complicated nonlinear function, and we don't want to spend the time vectorizing all of our functions in our tests. And again, if I don't want to compute a gradient and I want to compute a Jacobian, it's just a matter of changing a few characters and I get what I want. So I think this is really, really convenient and very easy to reason about. And that's it for me. And I'm going to give it up to June, who's going to talk about meta gradients.
Thanks. Hi, everyone. I'm June. I'm a research scientist at DeepMind. And I'm going to briefly talk about how I use JAX for my recent work. Next slide, please. So in this work on discovering reinforcement learning algorithms, we try to meta-learn a reinforcement learning update rule from a distribution of agents and environments like this figure. But there were several technical challenges because of the unique problem setup over here. Next. So first, we wanted to simulate many independent learning agents where each agent is interacting with its own set of environments. But this is already quite unusual because normally in reinforcement learning, we just consider one learning agent. But here we wanted to simulate multiple lifetimes of agents simultaneously. Next, please. And at the same time, we wanted to apply the same update rule, which is the meta learner, to all learning agents in a completely synchronized way. Next, please. And also, we wanted to calculate meta gradient over this agent update procedure, which requires calculating the second order gradient. And finally, we wanted to massively scale up this approach by increasing the number of learning agents without introducing much extra computational cost. So these were quite challenging. So to address these challenges, we used JAX, and JAX actually allowed us to easily handle all these challenges. So in the next slide, I'm going to briefly describe how we implemented this system using JAX. And at the beginning, we first implemented every environment in JAX so that we can apply Vmap and PMap later. And then, as you can see from this figure, we implemented a single update rule and single agent and single JAX environment interaction, which was quite simple. And if you go to the next slide, we added a Vmap to implement multiple JAX environments for one learning agent. And in the next slide, we added another Vmap at the outer scope to implement multiple learning agents like this figure, where each agent still interacts with its own set of environments. And finally, we added PMap to implement multiple copies of the same computation graph and then distribute this across multiple TPU cores like this figure with a shared update rule. So in this figure, each TPU core essentially has its own set of agents and its own set of environments, but they all share the same update rule, and they all calculate the meta gradient in a completely synchronized way and then perform meta update. If you go to the next slide, this is the pseudocode of our algorithm. So here, the top part implements the agent update, and the bottom part implements the meta gradient calculation. And the yellow part is the Vmaps and PMap that I mentioned in the previous slides. So if we just remove these Vmaps and PMaps, then it essentially becomes the single agent update rule environment interaction. But by just adding a few Vmaps and PMaps like this figure, we can easily convert the simplest single interaction implementation to the massively parallel system that I showed in the previous slide. So in the actual experiment, we used 16-core TPU, and using this TPU, we could simulate 1,000 parallel learning agents and 60,000 parallel environments with one global shared update rule. And we were able to process more than 3 million stats per second using 16-core TPU. So next slide, please. To just summarize, we had several interesting challenges because of this unusual problem setup. But by using JAX and TPU, we were actually able to handle all these challenges quite easily without putting much engineering effort, which was quite nice for us. And also we got quite interesting results out of this project. So if you're interested in this project, please check out the paper and also come by the poster session tomorrow. Yeah, that's all I have. Thanks. I'm going to hand over Fabio and Steve.
Hi, everyone. So I'm Theo. I'm a research scientist at DeepMind, and I'm going to present some work we're doing on search and model-based RL with Fabio. Next. Okay, so here we're shifting gears a little bit. So far we have looked at applications of JAX which crucially leverage its gradient computation capabilities. And you may ask, is this the main use of JAX? Is this gradient kind of based computation the main thing that we care about? And so here we showcase another application where JAX enables fast research iteration that uses gradient, but it's not the core of the compute. And it's basically multi-color research in a model-based RL setting, seen in AlphaZero or mu0. So we are training RL agents which plan effectively using an internal model of the world, create the form of a plan, which is a sequence of action that they optimize over, and then both use that plan to act in the real world as well as to update policy priors that they use to help to guide the plan. And there are challenges in doing so. The first is that in a typical kind of neural network guided tree search, you have a tight integration of the control logic and neural network machinery, and this is actually quite tricky to debug. There's challenges around scalability and parallelism because tree search is inherently a sequential algorithm. Fabio will mention more on this later. And as typical for model-based RL setups, there is a lot of issues around the data pipelines, a lot of not so much issues as much as design choices, the use of replay, the share of synthetic data versus real data, how to use data for policy learning versus model learning, and so on. And so you need a framework which enables you to quickly test loads of different ideas in that kind of setup. Next slide. So next, yeah. So and next again, thank you. So sorry, just one before, just the picture of it all. So in the last few years, we've seen kind of an explosion of a space which finds itself at the intersection of search-based algorithm, which evaluates a different type of solution using kind of more discrete type of reasoning, along with neural networks. So this has been found in work applied to games such as Go or Atari, or puzzle games like Sokoban, as well as robotics, chemical design, robotics, and so on. Next slide. And the particular algorithm that we investigate and replicate is mu0, which is an extension of AlphaZero, which learns a model of environment. It's a paper from last year, which obtains a state-of-the-art result on a variety of games, such as chess, shogi, Go, or Atari, and again, has a learned neural network model of the environment. Next slide. So I'm going to give a very quick introduction of neural network guided MCTS as it is done in mu0 to give some kind of context around the issues. So each MCTS consists of several simulations that happen one after the other. And each simulation consists of 3 steps. The first is you traverse the tree. You already have a given tree, and you're going to traverse the tree from the root to a leaf node using a chosen heuristic. In alpha or mu0, the heuristic is called PUCT, and it basically picks node with the highest score, where the score combines 3 factors, which is a policy prior, which is kind of a gut feeling of what is the next best action, action values, which are derived from the tree computation, and an exploration bonus, which is derived from visit counts, how often you've been in a particular node of the tree. So you keep going down next. You keep going down the tree until you reach a leaf, and eventually you reach a leaf node and then you add a node to the tree. Next. So this is called the expansion, and this is the case where you actually call the neural network because you need to compute the state transition from the leaf node to the new leaf node. You need to compute a value for that state and the policy prior for that state. And all of these consist in calling different neural networks. And eventually you cache all that computation, put it in the tree, and you follow by the backward step, which to propagate all that information from the new leaf node to all the ancestors in the tree. So this is basically how neural network MCTS works. And next, I'll let Fabio explain the issues around implementing MCTS in JAX.
Yeah, so hi, I'm Fabio. I'm a research engineer at DeepMind. So, so why is implementing MCTS like efficiently like a challenging task? Well, in the use case like we have in mind, like it is hard because you know, some of us researchers don't really want to use C++ day to day, and we'd rather use like higher level languages such as Python. But sticking with plain Python, performing MCTS in batch can be quite slow. Making like our research pace slower. And furthermore, as Theo mentioned, like vanilla MCTS is essentially a sequential algorithm, which puts even further constraints on how much we can parallelize computation. There is, of course, work in this space, but let's stick with the simplest possible scenario. So one possible approach to tackle all of the above is to rely on just-in-time compilation to somehow try to bridge the gap between interpreted and compiled languages. And this is very well aligned with the programming paradigm in JAX. The next slide. So off the bat, like if we decide to stick with JAX like we did, there are some expected advantages and disadvantages we can foresee. In particular, what we expect is that once we manage to JIT computation, we're going to be quite performant, at least compared to plain Python. Something that is really relevant for us, especially in RL, is to saving costs moving data in and out of accelerators, which would happen if you broke out to search in C++ on CPU. This in turn allows to, if you can, JIT search, you can JIT the whole acting and the whole learning of RL agents, which is really relevant for performance. Furthermore, we said that if you can stick to something that looks a lot like NumPy, it's going to be easier to reason and write and modify search components. Also, you can build on top of the JAX primitives that Michaela and others discussed today to write your code for a single example and then use, for example, Vmap for vectorization. Furthermore, there is this huge potential of being differentiable all the way through. Next one. On the flip side, this is going to be very likely less efficient if you are not batching. For example, if you want to deploy a trained RL agent on a single environment setup. And also, if you are giving up some of the compute and memory of your accelerators for search, you're going to have a bit less for plain inference. And this is going to have a further impact on how deep you can go with your search, because your search depth will be limited by the accelerator memory. Furthermore, if you're running all the searches in parallel, your performance will be constrained by the slowest instance of your search. I want to conclude by just showing a couple of code snippets. This is very high level, but I think it will kind of nicely reflect what we discussed so far. So this is like an implementation of the search method on our MCTS JAX class. As you can see, it is very nice and easy to isolate like the three main components of the algorithm, which is the simulate, expand, and backward function that you can easily play with as long as they are a nicely JITable function. I also want to highlight that the control flow must be expressed using like the JAX Lux library. For example, this won't be like a plain Python for loop, but it's going to be a for I loop. And furthermore, if you want to JIT, you need to make sure to have like a fixed shape in place. So you need to pre-allocate your data structure where you contain all your search statistics. Next one is an example of the expansion function, where everything that is to do with neural networks can be nicely wrapped into the single function call of the recurrent function, as it is in Mu0. And this, again, makes it very easy to break down and focus only on the few bits you want to do research on. And now we can move on to questions and debate.
Can we just ask questions? Okay, so so the most obvious question, I guess, is how does JAX compare to pre-existing or established languages like PyTorch or TensorFlow? So what would be the optimal scenario for JAX versus PyTorch, for example? What benefits would I have if I chose JAX over PyTorch?
So that's an excellent question. And I think that part of it would certainly be flavored by a personal perspective, but we also have members of the JAX core team here today. And I think that they would also, they should have first dibs on answering. Matt, JJ, Sky, or do you have an answer? Or?
I can say some things at a high level. I guess we think PyTorch is really great, and TensorFlow is really great too. A lot of people are really happy with those things, and you know, we don't want to cast, you know, sort of frame things in like a zero-sum way. I think there's things that PyTorch does that are better than what JAX does, and there are things that JAX does better. I'm more familiar with the JAX side, so I can say some things about what we are trying to do with it and ways in which those things might help you. So I think as folks talked about in these talks, JAX makes a bet on functional programming. That means that to the user, things end up maybe being closer to math, and that's nice. But also it means that JAX can provide some capabilities that work really well around like automatic batching, like Vmap, this sort of thing. Fancy autodiff. We started building JAX because we worked in automatic differentiation, and so I think JAX still has a lot of cool features like forward mode and reverse mode. They're composable. The way it interacts with Vmap to be able to compute Jacobins and Hessians really fast. It has some experimental features about exponentially faster, very high order autodiffs. You want to take like 100th order Taylor expansions. It's quite good at that. These are things that are like afforded by, in part, sort of betting on functional programming. And so you get sort of these transformations. So I say JAX is about the transformations, maybe first and foremost. Maybe, another thing to say is that it's very compiler oriented. I think Mihaela mentioned that she likes being able to dig into the guts of an optimizer and say there's not going to be an optimizer kernel like an Atom update op that's in C++. It's all sort of in user level Python, and that's because JAX is sort of designed around being compiler oriented, and that also like means that you can do some things well, like stage out entire parts of your computation. We had a entry at this is kind of the extreme end, not necessarily what you see yourself every day, but JAX had some ML-perf entries that set world records for training some neural networks extremely quickly, like English-German neural machine translation training in like 16 seconds. That's sort of like the extreme end of being, but it comes out of being sort of compiler-oriented. Like JAX is based around being able to like stage out, giving you the control to stage out parts of your program from Python, hand them off to this like XLA super optimizing compiler that can project things onto not just your GPU, your single card, or your 8 GPUs, but also like entire TPU supercomputers. Anyway, so I'd say like at a high level, the bet around compilers, things around functional programming and just being focused on providing many transformations and even allowing experts to sort of extend the system of transformations. I think those are things that sort of set JAX apart from how other systems have worked before. Whether that is actually useful to you, it depends. Maybe what's most useful to you is having a ton of example code out there, or having a really big community, or there's some workloads that might perform better in other frameworks, for example. But hopefully that gives you some flavor, along with all the other things folks have talked about here, of where JAX could be useful.
Yeah, Dankeschön.
Maybe I just wanted to add very briefly before we move to the next question a couple of things. So just one aspect is that JAX is comparatively very thin, is very focused on doing a certain range of things and do them very well. And I think that can be quite appealing if you really want to dig into and have like full control about what is going on. The fact that you can really delve into JAX and basically get a good understanding of how everything is working, because it's fairly compact and is only doing a focused set of things well. I found that personally very appealing, and it might be something that resonates with other people. And second, I just wanted to, again, Matthew already touched on it, but this functional programming style that allows to basically expose all the primitives in terms of composable function transformations has been like incredibly powerful, at least for me. I think June example to me is I worked with him on the project, has been one of the most eye-opening for me experience, because we literally just wrote a single agent interacting with a single environment and just dropped in a couple of Vmaps, a couple of Pmaps, and suddenly we were running a massive experiment across multiple TPUs and multiple environments and multiple agents. And so I just want to shout out again the power of composable function transformations, because it's really amazing.
Can you talk about the debugging experience? Like, what do you get when you inspect things, and also when JIT is involved?
Shall I take it? Yeah, maybe Mike. So the nice thing of debugging in JAX is that until you basically turn on JIT, you're literally just executing NumPy code, literally. Like it just looks a lot like it, and it actually executes a lot like it. So you can literally PDB into your program and step through it line by line and just check what the arrays contain and so on. And then you can basically just turn on the JIT to make it faster, but you can still debug everything in this kind of more friendly Python land. So I think the debugging experience from that perspective is quite nice.
If I could tack onto that, I think we're always looking for ways to improve. There's ways to have better error messages and track things. But on the subject of just being able to pop into a Python debugger, as long as you're not using JIT. So even things like autodiff, or even if you're using Vmap, so like something that uses both of those is the JAK forward function for forward mode Jacobians. And if you actually like have a function that you're taking a JAK forward of, and you put a debug statement in it, so you like jump into a debugger and you start printing values, it'll actually show you both the sort of like primal point at which you're linearizing and the entire sort of like basis of tangent vectors, sort of all the things you're pushing forward together, because both Vmap and this and autodiff work sort of in pure Python. I don't think it's necessarily the first thing that you think to do, but you do have all your values there. You can like poke at them and look at them. So hopefully that helps a little bit on the debugging front.
Awesome. So latest question, and I don't see any hands raised, but if folks want to raise hands instead of asking questions in the chat, we can also do that. So next question from Sherhill. Is there a TF data for JAX planned by either the JAX team or the DeepMind team? Oh, and sorry, apologies for that. Byron, Byron, it seems like you have your hand raised and are waiting to speak. Is that correct?
Yeah, but you can address the data one first.
Oh.
Also, sorry, the question is there plans for a TF data for JAX?
Yes.
Okay, well, one possible answer to that question is that actually many people do use TF data with JAX because you can just kind of go through NumPy arrays as the common interchange there. So there's like no fancy integration needed. You can really just use these like two libraries like any other libraries. So yeah, for that reason, and of course this applies to like other data loaders as well, or your own custom data loaders. So we don't have any immediate plans on the JAX team to like create our own data loading library. We think many other groups and teams have done a great job of this, and we don't know if we can do better. But yeah, I'm interested if there's any particular use cases or like features that aren't well served by the existing frameworks for data loading.
Awesome. Thank you, Sky. And Byron, go for it.
Cool. So first of all, excuse me. I want to thank both the JAX team and DeepMind team because I've been using sort of Haiku to re-implement some things in RLAX in the last several months. I've really enjoyed it. Like I think, as Matteo said, like just the functional format of it, I find it really exciting. And one thing that I don't think anyone mentioned, but I found really nice, is serialization of model parameters is super, super, super easy, right? Like if you just have your params out, you just save off your params. You load them back in, you're done. There's nothing you have to worry about with like fancy loaders or anything like that. So I really like that capability as well for checkpointing. It's really nice. But my one question I have is, again, having worked on this, can you guys just speak to like what the model is for contributing back to these projects? For instance, like I noticed you don't have bidirectional RNN support, so I had to roll my own. So what is in Haiku? What is the process for contributing back?
So maybe I can take the questions for the JAX ecosystem libraries. Maybe someone for the JAX team can say more about contributing to JAX core itself. We are definitely open to contributions. So we have already taken quite a few contributions, both in RLAX and OPDX, for instance. So I think that the main message there is open an issue on GitHub, and let's have a conversation there. I guess it's hard to say without knowing the details. We try to we have an explicit aim to keep each library quite focused and similar to how JAX core does one thing and does it well. Similarly, in our ecosystem libraries, we try to have OPDX focus very clearly on optimization, Haiku very clearly on neural networks libraries, reinforcement learning Relax very clearly on reinforcement learning. So there might be cases where maybe there might be valuable code that doesn't fit quite exactly one of the ecosystem libraries, in which case might be we might have to make a call in sense of whether or not it fits the scope of each library. But definitely, I think opening an issue on GitHub would be a nice way of starting a conversation.
Excellent. Matt, is there anything that you wanted to add, or Sky or Tom?
We like, we love open source contributions. So yeah, come over to our GitHub and try to make them. Yeah, +1 to everything Matteo said. We actually just had someone added like Windows building support, I think, and that was incredible. That was like a issue number that we had in like the single digits, and some open source contributor just contributed it. So that was fantastic. So yeah, come to our issue tracker. We're often like overloaded and like time limited and stuff. So if we don't respond, it's not lack of interest. It's just because we're scrambling with other things. But yeah, we love seeing people start discussions and make contributions.
Cool. Excellent. It looks next up looks like Horace.
All right. Yeah. So I guess I kind of wanted to ask more about the debugging issue, or like the debugging topic. So, so I get how the like in general, like with eager mode JAX, it's easy to debug because you can just use all your regular tools. But in the presence of transformations that aren't like JIT, does it still remain easy to debug? Like I guess what happens if you have like a print statement and then you like call grad or vmap and on it? Like, yeah, I guess can you talk about that?
It's a great question. That's sort of what I was getting at, but maybe it's sort of hard to explain in words without, showing the code. But JAX works by tracing mechanism, and that means that it's sort of propagating extra values inside your Python code. And so if you print out if you have a function and you print out an intermediate variable in it, and then you call grad of that function, you'll see something print out, and JAX will sort of like show you the information that it has going on under the hood. So, you can use PDB to debug things. You end up looking a little bit, behind the scenes, like under the covers of what JAX is doing. So, in the grad case, for example, you'll see some, string that prints out when you print a value that shows sort of the primal value at which you're linearizing your function, and then something, depending on if you're using forward mode or reverse mode, possibly about the tangent value. That's a bit in the weeds, but I guess like, a lot of JAX, stays in Python. JIT stages things out, but for the things that stay in Python, we try to make the debugging experience as reasonable as possible. So Vmap as well is another example. You can actually, if you print out the value of an intermediate thing in a Vmapped function, then it'll actually show you sort of the value it's keeping behind the scenes that has that full batch dimension. Even though like your code thinks it's operating on single examples, if you print a value, JAX will say like, actually, I'm hiding a whole batch of examples behind the scenes here. But all that said, those are just ways in which we've tried to make the Python debugging experience work. I'm sure there's lots of ways that it could be improved still as well.
Excellent. Thank you, Matt. And thanks everybody for the questions. These are great. I think the next one is from Robin.
Thanks. Does it make sense to mix in a bit of JAX if you have an existing PyTorch application, or does it really make more sense to just always completely do one or the other?
I think it depends, on just a lot of situation-specific details and what kind of mixture you're talking about. But I think actually there's a lot of potential for interesting ways to compose things. One, small example is just being able to hand off GPU-backed arrays efficiently between the two without copies and without much overhead. That might be a nice feature if you actually want to write some parts of your program in PyTorch. You have a function that's backed by like PyTorch operations. Part of it that's backed by JAX operations. So I think both PyTorch and JAX implement the DLPack standard for sort of exchanging memory like this. And I think there's still some like caveats, like there might be like a GPU synchronization incurred or something like this. But other than sort of engineering details that folks are still working on, I think there's ways that we can make these things super compatible, and that way users just win, right? There's no reason to lock people in. If you have reason to build stuff together, I don't know exactly what those reasons are, or can't think of a situation necessarily off the top of my head, but we want to make it so that you can compose these things and you're not limited in that way.
Maybe I would just add that this kind of potential integrations might also be helped by the fact that JAX is quite focused and quite lenient. It's not like a huge vertically integrated framework where if you buy into one aspect of JAX, you need to buy in everything else and a specific neural network library and so on. So being quite lenient might open up, being quite lean might actually make this kind of integrations easier. Although it's hard, of course, to discuss without specific details.
Sky, actually, in your demo yesterday, was part of the Hugging Face demo like loading values from like PyTorch checkpoints or something?
Yeah, the BERT fine-tuning demo involved basically downloading from the Hugging Face BERT checkpoint in PyTorch and then loading it into JAX. But I think that probably went through NumPy arrays because it's like downloaded on the host rather than like through DLPack.
Perfect. So we have Horace. Did you have another question, or is your hand still raised from?
Sorry, no more questions from me.
No worries. Are there any questions on the chat that we didn't get a chance to answer? It looks like Julian answered Ulysses' question about performance. Avital and David shared great link, or James shared great links.
Robert has his hand raised now.
Excellent. Robert?
Hi. I had one question just regarding the future of JAX and what we can expect essentially from both the DeepMind internal packages as well as the core team.
Awesome.
I guess I can speak to the DeepMind part. So like in terms of our libraries, I think this model of having low-level libraries of components with incremental buy-in has been a real win for us. I think one of the natures of research is that it's broad and unpredictable and moves very quickly. I think often when we try to go the other way and sort of plan in advance, what we think we need to build in terms of like a press play and run framework. By the time we've gotten there, sort of the field has moved on. I think by having these frameworks components, I mean, perhaps an individual component someone contributes is not as relevant as it was in the past, but it doesn't sort of affect your ability to sort of build others or contribute or expand or whatever it may be. So certainly this idea of trying to sort of identify the core features that are required in our research, contribute it back, use this as a substrate of sharing research throughout the organization and to the broader community as well, and is adding more libraries and building libraries on top of libraries. I think this is working really well for us and something that, at least in the short to medium term, we intend to continue.
Maybe someone from the JAX team can answer the question in regard to JAX core.
Yeah, I can say something, but someone else from JAX core interrupt me if they have a really good answer. I never quite know, what it means to, answer a question like that, other than to say that like the folks who are working on JAX, myself included, like we love this project. We're like pouring so much of ourselves into it. And so, that to me, that's sort of like as much of a guarantee of it's not going away as you can get, just because we're personally very invested. I guess the JAX team has grown, and so and it's working well at places like DeepMind and Google Brain and research more broadly. So I don't think anyone wants to like. I think everyone is the best days of JAX are ahead, I guess is what I'm saying. JAX is growing. The folks working on it are very passionate, as you've seen, and so I wouldn't worry at all about JAX going away or something like that.
Awesome. And we are at time, but we might have time for one more question. And it looks like Robin had his hand raised.
Yeah, this looks amazing. I was wondering, what do you think are the stumbling blocks that new people to JAX often hit upon? Like, are there certain things that are more that are often confusing for people or cause issues when they're just getting started?
We have a great link for that. There's something called the JAX, the Sharp Bits collab on the docs. I'll link that in the chat.
In addition, I guess I'll add one from the DeepMind side. I think sort of, as like one of the strengths obviously of JAX is this this bet on functional programming and sort of raising everything to a functional paradigm where things are stateless and you don't need to worry about side effects. I guess as an organization, I guess we decided to sort of diverge from that slightly with some of our libraries, such as Haiku. And the reason was we had other considerations that we needed to balance. We had so many users that were already using Sonnet as their way of defining and reasoning about neural networks within TensorFlow, and we really wanted to be able to maintain that API. So certainly there's some cognitive overhead in sort of writing something that looks object-oriented, which is sort of converted for you into functions, and sometimes that takes some users some time to ramp up to. But I mean, that was just sort of the trade-off that we decided worked for us as an organization. Certainly there are other JAX neural network libraries that take different approaches that other people find work better for them. And in the spirit of incremental buy-in and cross-compatibility, you're free to use any part of any of those with any of our other libraries as well. I think for the most part, that's been working for people.
Thank you.
I would add maybe a common bit that was also mentioned on the chat is the pseudorandom number generation. That is something that as a first newcomer to JAX might be a little bit surprising if you're used to NumPy, where you don't have to reason about the state of the random number generator almost at all. I would say, though, that while it can be surprising at first, it actually pays off in the long run. So once you get used to actually this way of dealing with random number generation, I think, and in some sense, at least personally, I kind of ended up with the conclusion that this was actually the right way all along, in some sense, and that there is also a very nice document in the JAX documentation about the PRNG design, explaining the reasons and the motivations for the way JAX deals with random numbers. I think that is a great read. I think as a newcomer, if you're maybe a bit puzzled at the beginning by random numbers, just read that doc, because it will I think clarify a lot.
Yeah, I wholeheartedly agree with what Matteo is saying. Like, once you've used JAX RNGs, like all other RNGs that maintain their own state silently become very scary all of a sudden. So definitely.
Cool. So so we are at time. Thank you all so much for your questions. There might be one more slide left. Is this correct, Matteo? Haha, there we go. Cool. So thank you everybody for coming. Absolutely, please make sure to share your JAX projects on social media, whatever your favorite flavor of social media is. GitHub is also social. And it is my favorite social hangout place. But anything that you create, please tag it with JAX ecosystem so that we can make sure to see it and to share it. And if you're interested in contributing, there are many issues that are good for first contributors on the JAX repo, many places to get involved, and we look forward to seeing what you create. Thank you so much, everyone, for attending. Thank you to JAX Core and for all of the JAX ecosystem teams for presenting your work and for getting us all very excited. I know I am significantly more excited somehow than I was even an hour ago. So thank you, everybody. Have a great day. Have a great NeurIPS, and see you soon.